In this video, we're going to look at linear second-order equations with non-constant coefficients. We're going to look at two methods for approaching non-homogeneous linear equations with non-constant coefficients. The first one we're going to look at is very specialized. It's a Cauchy-Euler equation. This linear homogeneous ODE with non-constant coefficients always has a solution that can be found. This particular type of this form is called Cauchy-Euler, and it looks like this. We have this a, which is a constant, t squared, x double prime of t, b t, x of t prime, and c of t, x of t is equal to 0. A, b, c are real numbers. A does not equal 0. Dividing everything by t squared and a, we'll get x double prime of t plus b of a over t, x prime of t, c over a t squared x of t is equal to 0, where obviously t cannot be 0. It's very, very specialized linear homogeneous ODE with non-constant coefficients. Now, if we let s equal the natural log of t, then t would equal e raised to the s, and its derivative would be 1 over t, which is e raised to the negative s. If y of s is equivalent to x of t, and we're talking about capital Y of s is equivalent to y of t, then y can be a function of s, and the chain rule can be used to compute this x prime of t. And similarly with the x double prime of t. What we end up with is x double prime of t is equal to the derivative with respect to s of y prime of s, e raised to the negative s ds dt, where x prime of t is equal to y, or dy ds dt, which is y prime of s e raised to the negative s. And what we end up with is, when we get totally done, is this particular linear homogeneous ODE with non-constant coefficients can be wrote as a double prime of s plus b minus a y prime of s plus c y of s, which is equal to 0. Then we get a really nice characteristic polynomial of a r squared plus b minus a r plus c is equal to 0. And we get some rules about the discriminant of this characteristic polynomial. If k is greater than 0, if the discriminant is greater than 0, and they're not equivalent roots, they're not repeating roots, then we have x of t will be a c sub 1 t raised to the r sub 1 plus c sub 2 t r raised to the t raised to the r sub 2. If we have repeating roots, in other words, our discriminant is equal to 0, x of t will be equal to c sub 1 t raised to that repeating root plus c sub 2 the natural log of t, t raised to that repeating root. If I have a discriminant that is less than 0, my complex roots will have the form of alpha plus or minus beta I, where x sub t is going to be c sub 1 t to the alpha cosine beta natural log of t, c sub 2 t alpha sine beta natural log of t. So we're going to start out with finding the two solutions of the homogeneous equation and then use a variation parameter to find x of p. So the first thing we're going to do is find our homogeneous or complementary solution. And to do this, I'm going to need to find my characteristic polynomial. And notice it is of the form of the Cauchy-Euler. And you're thinking, wait a minute, isn't that missing a middle piece? Well, it is. So let's deal with that, and let's divide everything by t squared. So let's rewrite this as x double prime of t plus 0 divided by t x prime of t, and then minus 2 over t squared x of t. And this will equal to 2 over t. We have a is equal to 1, b is equal to 0, and c is equal to 2. So then what I have for my characteristic polynomial is r squared plus 0 minus 1 r minus 2, which is equal to 0. And I have k, which is equal to 1 minus 4 multiplied by negative 2 multiplied by 1, which is greater than 0. So we know that we're going to have two distinct roots. And in particular, when I take my characteristic polynomial, which is r squared minus r minus 2 is equal to 0, this factors into r minus 2, r plus 1 is equal to 0. Based on the chart above, then my x sub h, my homogeneous solution, would be, I have c sub 1 t raised to the 2, because this would be r is equal to 2, excuse me, not t, r is equal to 2 and negative 1, and it doesn't matter which one you put first. And then my second one would be c sub 2 t raised to the negative 1. Now I'm going to go ahead and do my Wronskian, which gives me t squared 2t, t raised to the negative 1, negative t raised to the negative 2, and I end up, when I get totally done, with the number 3. So then I would have my v sub 1, using the variation of parameter, is going to be the negative integration of 2t raised to the negative 1 multiplied by t raised to the negative 1 over negative 3 dt, which ends up becoming negative 2/3 t raised to the negative 1. My v sub 2 would be the integration of t squared 2t raised to the negative 1 divided by negative 3 dt, which gives me negative t squared divided by 3. So then my x of t would then be c sub 1 t squared plus c sub 2 t raised to the negative 1 minus 2/3 t raised to the negative 1 minus 1/3 t. And my final solution, cleaning this up a bit, is c sub 1 t squared plus c sub 2 t raised to the negative 1 minus t. All right. So, and this should not have negative 1. Just want to erase that because of the fact that I would multiply my v sub 1 by its x sub 1 and my v sub 2 by its x sub 2, which is why I have negative 2/3 t minus 1/3 t, which gives me a negative t. Let's take a look at my next example here. And once again, I need to divide everything by t squared. And when I divide everything by t squared, I'm going to get x double prime of t minus 2 divided by t x prime of t, and then plus 2 over t squared of x of t, and this is equal to 3 over t. So then my a is 1, my b is negative 2, and my c is 3. My characteristic polynomial is r squared minus 2 plus minus 2 minus 1 multiplied by r plus 2, which gives us r squared minus 3 plus 2. And so this factors into r minus 2, r minus 1 is equal to 0, So my x of h of t, my homogeneous, is going to be c sub 1 t raised to the 1 plus c sub 2 t raised to the 2. I'm going to do my Wronskian, where I have x sub 1 is equal to t, and x sub 2 is equal to t squared, and my function f of t is equal to 3 divided by t. Doing my Wronskian, I'm going to end up with a t squared. My v sub 1 is going to be negative the integration of, so I'm going to have t squared multiplied by f of t, which is 3t multiplied by t squared dt. My v sub 2 is going to be the Wronskian the integration, excuse me, the integration of, let me see, it'll be 3 times t divided by t squared dt. This ends up becoming a negative 3. The natural log of the absolute, or natural log of t should be absolute value, but we're just going to let that ride for right now. And v sub 2 is just going to be negative 3 divided by t. Now, my x sub 1, or my x of t, would then be equal c sub 1t plus c sub 2t squared minus 3t, 1 plus the natural log of t. And do I have any initial values on this? Nope. That's pretty much it. Oh, and the reason I ended up with this is, remember, I multiply my v1 and my v2 by the appropriate x sub 1 and x sub 2. And then, of course, I can factor out a negative 3, leaving me this. Now, let's take a look at this example. We're going to solve this initial value problem and sketch your solution between 0 and 3 for t. Now, the great thing about this one is that it's already set up in the form that we want. And because this is already set up in the form that we want, then all I have to do is figure out what A, B, and C is. So I have A is 1, B is 1/4. Oh, no, sorry, B is 0, excuse me. B is 0, because it's like the first one, B is 0. And C is equal to 1/4. So when I find my characteristic polynomial, it will be, just like it before, r squared plus 0 minus 1, 0 minus 1 r, and then plus 1/4 is equal to 0. If we multiply everything by 4, we're going to get 4r squared plus 4r plus 1 is equal to 0. So 2r plus 1, the quantity squared, is equal to 0. So we have a repeating root on this one. And so I have r is equal to 1/2. Using the chart up above, I'm going to have x sub 1 is going to be equal to t raised to the 1/2. And then x sub 2 will be equal to t raised to the 1/2, the natural log of t. My Wronskian is going to be 1. My v sub 1, when I get done, is going to be negative t squared divided by 2, the natural log of t, plus t squared divided by 4. Excuse me, my v sub 2 is going to be t squared divided by 2. That means x sub p is going to be equal to v1 x1 plus v2 x2, which when I get totally done is just going to be t raised to the 5/2 divided by 4. So that's kind of nice. Then my x of t is going to be equal to c sub 1 t raised to the 1/2 plus c sub 2 t raised to the 1/2 natural log of t plus x raised to the 5/2 divided by 4. Now we know that x sub 1, or x of 1, is equal to x prime of 1, which is equal to 0. We're going to get c sub 1 is equal to negative 1/4, and c sub 2 is equal to negative 1/2. So then the particular family member I am searching for is negative 1/4 t raised to the 1/2 minus 1/2 t raised to the 1/2, the natural log of t, plus t raised to the 5/2 divided by 4. Okay, now let's talk about the second way to solve these. Series solutions. Before computers, there was a standard analytical method, such as the famous Bessel's equation. Solving using a series which involves a Taylor and Maclaurin series from Calculus 2. If you are programming to solve ODEs, then read through this section and refresh the Taylor and Maclaurin series from your Calculus 2 book. If not, use an online tool to solve these types of ODEs. The end. And that's it for this video.